Exponentials. F of x equals some base to the power of x. Look in this specific example, f of x equaling base 2 to the power of x. If x is equal to 0, I'm going to have 2 to the power of 0, which will be 1. Anything raised to the power of 0 will be 1. So for all of these exponentials, you'll see them coming through the point 0, 1. Because if you take a base and you raise it to the power of 0, the result will always be 1. If x is equal to 1, then you're going to have the base to the power of 1, so you're going to get a result of just the base, and in our case, that'll be a 2. So 2 to the power of 1 is 2, and we get that position. What you'll also see is that as x increases, so as x approaches positive infinity, the value of y approaches positive infinity. As we move in the negative directions, as x approaches negative infinity, you'll see that the value of y approaches 0 from above, and we can write that as being 0 with a little plus symbol above it. Here we have f of x equaling e to the x, where e is Euler's number, and it's approximately equal to 2.71. Same shape, but what's interesting here, again, is that if x is equal to 0, it will be e to the power of 0, which is just 1, so it comes through the position 0, 1. But when x is equal to 1, I'm going to have e to the power of 1, which is just e. And as I said to you before, that's approximately equal to 2.71, so that's why it's shown there. Please note, at no stage with these exponentials hit the x-axis, so we have a horizontal asymptote at y equaling 0. But of course, there's variations on these basic graphs. We can apply transformations just like we did with those other functions. The big difference with the exponentials is that we can either have an increasing or a decreasing exponential. If the base is greater than 1, then we're always increasing. So think about it. If we have a base of 2, 2 to the power of 0 is 1, 2 to the power of 1 is going to be 2, 2 to the power of 2 is going to be 4, 2 to the power of 3 is going to be 8. So you can see it's increasing. If I consider a decreasing exponential, that's achieved when the base is greater than 0 but less than 1. So we're basically looking at a positive fraction. Let's use the base of being a half. A half to the power of 0 will be 1. Half to the power of 1 will be a half. Half to the power of 2 will be a quarter. Half to the power of 3 half to the power of 3 will be 1/8. So you can see it's decreasing. Transformations can be applied just as what we're used to before. So A, K, and this time I'm using B instead of H, and C. All those transformations apply. The big one here, vertical transformation, up and down. K, remember the dilation factor is 1 over K. Horizontal translation, take what's in the brackets here, make it equal to 0, solve for x, and that will tell you the horizontal translation. This just highlights if I've got the basic f of x equaling 2 to the x, the effect of the 3, every y value on this original graph has been multiplied by 3. So as an example, position 0, 1 is now going to become 0, 3. The effect of the 4, everyone on this original graph has been multiplied by 4, so the 0, 1 is now going to become 0, 4. You can see the shape. This time we're looking at the effect of the k. So the standard graph, f of x equaling 2 to the x. So what if I have a dilation factor of, or what if I have a 2 directly in front of it, or a half directly in front of that x? And the differences are shown here. Remember, everything cuts through that 0, 1 for all of your exponentials. So if we consider from there to there, then what's actually happened is that the value in front of the x is a 2. That indicates a dilation factor of a half. Remember, it's 1 over. So it's a half parallel with the x-axis. That is that every x value on this original graph, this dark blue graph, has been multiplied by a half, just the x parts. So as an example of 0.12 is on this graph, that is going to become a half 2. So what was there is now going to become there. Here we have a half immediately in front of the x, so x divided by 2 can be reorganized, so it's a half times x. So the dilation factor will be 1 over a half, which is 2, so every x value has been multiplied by 2. So a 0.12 on the original here is now going to become 2, 2. So that's why it's creating that shape. We're reflected in the x-axis. What will that look like? So you can see that just there, not too hard to digest. Reflected in the y-axis. So if all of a sudden we had a negative in front of the x, you can see what was an increasing exponential will become a decreasing. Vertical translations, no big surprise, just moving it up and down. Horizontal translations, are not a big surprise again. Take that power there, x minus 3, make it equal to 0, solve for x, means 3 units that are positive. So we just take that original graph, we're picking it up, and we're moving it 3 units along. Looking at some examples now.
Find the equation of the asymptote, the y-intercept, for the following. Hence, sketch the graph and state its domain and range. And we should write this in the simplest index form where applicable. Okay, so the first function, the rule is f of x equals 2 to the x plus 5. What does this part here mean? It means that the value of x can be any value that belongs to the real set of numbers, and it can map out any value for y that belongs into the set of all real numbers. Okay, so it's just letting us know that there's no domain restriction. So first of all, basic shape. The base is 2, and that's greater than 1, therefore we've got an increasing exponential, which will look like this. Horizontal asymptote is at y equaling 5. So it's just based on that. Y-intercept, we just simply sub x equaling 0 into the rule, and we establish that 0, 6 is the y-intercept. So I rule up my Cartesian plane, I put in my horizontal asymptote, I mark in my y-intercept, and then I follow this shape. Done. B, we've got f of x equaling 3 to the power of 2 minus x, take away 5. So the base is 3, again that's bigger than 1, so we have an increasing exponential, this shape. Horizontal asymptote is y equaling negative 5. The y-intercept, I have x equaling 0, and it produces 0, 4. For my x-intercept, I make y equaling 0, and I need to solve for x. At this stage, you don't have the skills to do this. Later on, we'll talk about logarithms, and I'll show you how that works, and we can evaluate this, but at this stage you don't, so we don't need to place that in. But it will cut through somewhere along the x-axis. So I put all my information in. Here's my intercept. Here's my asymptote. That there is my y-intercept. And so I draw this through. It will come through and down there. So it's probably not a good drawing there. So in yours, can you please make sure that it cuts through there, but also it cuts through your x-axis and then starts approaching that asymptote. My domain set of all real numbers, so x can be anything, and the range, I've got y being greater than the asymptote, so y is greater than -5. C, this time I've got f of x being a half to the x plus 3. So taking a look at that solution. A is a half. That is greater than 0 but less than 1. So therefore we're talking about the basic shape being a decreasing exponential. So this time it's like so. Horizontal assy will occur at +3. So I've got y equaling 3 here. It's my horizontal asymptote. Y-intercept, sub in x equaling 0 to produce the point 0, 4. So I place that in, and then I draw in that basic shape. Of course, at no stage is it going to cut through the x-axis, so I don't need to evaluate anything there. In some cases, we may need to evaluate what x is in an equation like this. 2 to the power of x minus 3 equals 10. All we need to show are these steps. Later, I will show you how to use logarithms to find out exact values, but at this stage you don't have those skills. So to work out what x is, we need to use a solve function on our CAS. Menu, algebra, solve, and we had 2 to the power of x minus 3 equaling 10. And I'm solving for x. I get that as an exact answer. This means the natural logarithm of 80 divided by the natural logarithm of 2. That's not very helpful to us at this stage, but if I go Control Enter, you can see I now got that approximate answer, which is more useful to us. And there's my answer given. So all you need to show is that equation, then what x is equal to. These are just the steps that you follow in your CAS. So in what situations would you need to use this? Can you imagine that we're after the x-intercept? Okay, so in an equation which is y equals 2 to the power of x minus 3 take away 10, to evaluate the x-intercept, I would make y equaling 0, then I'd add 10 to both sides, and then to solve for x, I'm left with this. And that is when you would apply menu algebra solve to work out that x-intercept.